Next physical quantity of this chapter we have power. How do we define a power? So power, it is defined as rate of doing work. What exactly do we mean by rate of doing work, right? Define is rate of doing work. It tells us with what speed the work was done. Let's say you are required to fetch a bucket of water from the ground floor to the fourth floor, right? Let's say four of you start doing the work at the same time. Now how will you measure that whose power is more? Because the work done by all four of you is same. You have fetched water from the ground floor to the fourth floor, so work done is same, the vertical displacement is same, hence the work done is same. But how will you compare? So that comparison now can be done in terms of the time, in terms of the physical quantity called as a power. Whomsoever has taken lesser time to take the bucket from the ground floor to the fourth floor has done more work, has got more power, not done more work, he or she has got more power. So rate of doing work, write a mathematical equation for the power, converting the same definition into mathematical form. Power, it is defined as work done upon time, right? At advanced level, you can also write in differential terms dw by dt. You may not be knowing what these symbols are and what do they mean, but at higher level the formula gets modified this way. This gives you the instantaneous power, the power at this moment itself, whereas this is the formula for the average power. You can also modify this way. This average power will be change in the work done upon time, that is nothing but W2 minus W1 upon T2 minus T1, and this is the formula for instantaneous power. Power produced by a machine depends upon, right? Here I gave you an example of the four of you who are required to fetch water from the ground to the fourth floor. So let's say the machine does the work. So power produced by a machine depends upon, so the first factor, that power is directly proportional to the work done. More work done, ultimately more power. And secondly, power is inversely proportional to the time. If you take more time to do a particular work, right, that means your power is less. I said whomsoever has brought fetched water with a more time, his or her power is less. From the formula itself we get these variations, right? Both of them are in numerator, so directly proportional. Power and time inversely proportional to one another. If the time taken is more, ultimately power produced by a body, right, or a machine will be less. Then next we have units of power, right? SI unit of the power is watts. Watts can further be written as, if you convert in terms of joules and second, power, right, it is also joules per second. Joules per second, in short, it is called as a watts. Watts, James Watt, he invented a steam engine. If we write it down in the fundamental form, so fundamental form, we have work done as kg meter per second square, and displacement, this is F. Work done is, this is the force and this is the distance, and divided by time. So force into distance and upon time. So this thing, if we simplify, it becomes kg meter square per second cube. This is the fundamental unit of the power. So watts, joules per second, in short it is called as watts, and in fundamental form it is kg meter square per second cube. For many further calculations, the fundamental forms are required. In CGS format, corresponding to joules, we have a CGS unit as arc, and the unit of time remains as it is in CGS format. So this is one unit. And in fundamental form, if you write down, gram centimeter per square second cube is the fundamental unit of power. We also have some special units of power. The one we have is horsepower. 1 horsepower, it is taken as 746 watts. To make our calculations simple, right, we round off this value to the nearest tens and it becomes 750 watts. So 1 horsepower is 750 watts. Then we also have a kilowatt. The word kilo means 1000, watt remains as it is. We also have a megawatt, right? Mega means 10 to the power 6 watt, right? We can also have a milliwatt. Milliwatt, your mobile phone, your electronic gadgets, they consume power in milliwatts, such LCDs, right? Televisions, microwave, refrigerator, air conditioners, they consume power in kilowatts. If I talk about this building, it consumes power in megawatt, right? Horsepower generally we use related to the engines, right? Car engines, you may say, locomotives, railway engines, you may say, ships, you may say, excavator machine, you may say, JCB machine, you may say. So all such machines, their powers are measured in horsepower. Milliwatt, as I said, electronic gadgets, it is 10 to the power minus 3. Milli means 10 to the power minus 3. So that is about the power. Next we have is energy. What do we mean by energy? Energy, it means ability to do work. Ability to do work. You are able to do work. You are able to fetch water from the ground floor to the fourth floor. It has only been possible. The work has been done by you only because you got an energy. You got the energy to do the work. So energy, in simple words, it is a ability to do work. Units of energy. SI unit of energy is joules and corresponding CGS unit is org. Now here you might be wondering that why the units of energy and work done are same. The work done also has a same unit and energy also has a same unit. So once again, if you recollect the example, right, that you have fetched water from the ground floor to the fourth floor. So you have spent energy and in turn the work is done. So energy is a theoretical discussion that yes, I have spent lots of energy, right? We may use words to express the energy that no, I'm not tired in fetching the water. I'm completely all right. I can fetch 5 more buckets. So energy means just a description of the work done in words. Whereas correspondingly, if you want exactly mathematical figure that how much energy you have utilized, then the work done is required. So work done and energy, they both are same. Energy is just a theoretical discussion of day-to-day activities, whereas work done is a mathematical calculation of day-to-day activities. You did a activity, right? Fetching bucket from the ground floor to the fourth floor. So you may explain in words that no, I'm not tired, I can fetch few more buckets. Someone may say no, I'm very tired, it was too much height to carry, my hands are paining. So that is the description of the energy spent. But if you do exact calculations, right, you will get a mathematical number which represents the work done. Energies we have of so many different types, right? We have a heat energy, we have sound energy, we have electrical energy, we have magnetic energy, we have electrostatic energy, mechanical energy. Mechanical energy is again kinetic energy, potential energy, nuclear energy we have. So since we have different types of the energy, if I use only these units, it's going to create quite confusion. Let's say if I tell you that I have 100 joules, I have 100 joules of energy. So what will you conclude? Which type of energy do I have? Do I have heat energy? Do I have sound energy? Do I have magnetic energy, electrical energy, right? Nuclear energy? Which energy I am talking about? So in order to avoid the confusion to the some extent, we have some special unit. One of the energy which we commonly use in our day-to-day life is a heat energy. So heat energy has been given a special unit. These are neither SI neither CGS. These are just the units, special units. Whenever I say or someone say or if you see written somewhere 100 calories, then you must conclude that it refers to the heat energy. It's neither referring to potential energy, it's neither referring to kinetic energy, neither sound, neither electrical. It refers to the heat energy. Heat energies we are always associated with whatever work we do, right? The food we eat, the energy we spend, everything we calculate in terms of calorie. You might have noticed your smart gadgets, smartphones, smart watches, They show how many calories you have burned. They show how many energy you have spent up in terms of the calories. So calorie is a special unit which refers to the heat energy. So one of the special unit of heat energy is calorie and other special unit is kilocalorie. How much calorie is how much amount of heat one calories, whether it's too large or too small. So we get that idea from its definition. Definition help us to understand the terminologies. It helps us to understand the unit over here. So experimentally, it has been found that 1 calorie, it is the amount of heat energy required to raise temperature of 1 gram of water by 1 degree centigrade. Just note this. To raise the temperature of 1 gram of water by 1 degree centigrade. How much is 1 gram of water? Hardly 1 spoon or 2 spoon, right? So for that much amount of water to rise its temperature by 1 degree, how much heat you will need? You keep it on the burner. As soon as you start the burner, for sure within second or half a second, the temperature will go high by 1 degree. So it's a very less amount of heat. When we say calorie, 1 calorie, it's a very less amount of heat. Let's see kilocalorie. 1 kilocalorie written as KCL, right? It is the amount of heat energy required to raise temperature of 1 kilogram of water by 1 degree centigrade. So now this seems very large. 1 kg of water, one full bottle of water, place it on the, take it into the container and start heating it with the help of the thermometer. Try to note that, let's say if the initial temperature is 26 degrees centigrade, how much time does it take to come to 27 degrees centigrade? For sure, it will take 1 or 2 minutes. So kilocalorie is quite a bigger unit as compared to calories. The smart gadgets, they show energy spent by you in terms of kilocalories. Then we have these relations which you must remember numerical point of view. 1 calorie is 4.2 joules and 1 kilocalorie is 4200 joules. Actually 1 calorie is 4.186, but most of the times we round it off and we use it as 4.2 just in order to simplify, to make our calculations little simple. And same way here also, 1 calorie, instead of 14186, we just round it off to the 4200 joules. Electrical energy is the another energy which we are quite often associated with, right? If not directly, indirectly, right? We use electrical energy in a household and almost in everything. So electrical energy has been given a special unit. First unit, we have a water. So how will you define a water? So 1 watt hour, it means 1 watt is joule per second. So 1 joule in 1 second, right? 1 joule second, and hour we have as hour, you can convert it into 60 into 1 hour is 60 minutes and each minute is 60 seconds. So converting hour into seconds, second said cancel, it is 3600 joules. So little larger amount, larger unit of energy, right? 1 watt hour. If this is a relationship with the joule, if you define the watt hour, right, it can be defined as when 1 watt of power, watt is a unit of power, right? So when 1 watt of power is consumed, that too in 1 hour, consumed in 1 hour, right? So just you can write it this way, can't frame more sentence. So it is 1 watt hour is using 1 watt of power in consumed in 1 hour. You can remember it this way. When 1 watt of power is consumed in 1 hour, we say electrical energy consumed is 1 watt hour. Or you can say when 3600 joules of energy is consumed we say 1 watt hour of electricity is consumed. Same way kilowatt hour. So it is kilowatt hour, again converting it into joules. 1 kilo, that is 1000, right? Watt means 1 joule upon second, and hour means 60 into 60 seconds. So this thing, if you simplify, it will become 36000000 joules, which can further be written as 3.6 megajoules, right? Mega means 10 to the power 6, just on the previous page I showed you. So to convert it into mega, multiply by 10, divided by 10. The numerator's 10 gets added up. So total 6 zeros means mega, and the denominator 10 gets converted into the decimal one. So when you use, right, 1 kilowatt of power is produced or consumed, you may say 1 kilowatt of power is consumed in 1 hour. This is the defined, means 1 kilowatt. Generally we use kilowatt, right? Watts also we use. The fans, tube lights, they consume energy in watts. Air conditioner you may take, washing machine you may take, microwave you may take, refrigerator you may take, they consume energy in kilowatt hour. They require more electrical energy for themselves to work. Then 1 watt hour is how many joules? Previously already we had seen it is 3600 joules, and 1 kilowatt hour is 36000000 joules. So it can also be written as 3.6 megajoules. Both the ways you must remember. Then energy of a moving electron. The units which we saw are the units for the energies which are quite large. But what about if the energies are very small? What would you say that the kinetic energy possessed by a ant? You see ant moving very slowly. So snail moving very slowly. So in such categories, how will you express their energy? So here we have a unit in terms of moving electron. We call that unit as electron volt. 1 electron volt, it is defined as when a charge of 1 coulomb moves across the potential difference of 1 volt. When you apply 1 volt and let's say 1 coulomb of the charge moves, you can further modify it as that 1 coulomb is nothing but 6.25 into 10 to the power 18 electrons. This many electrons they move, right, on applying the potential difference of 1 volt. Then we say that the 1 electron volt of energy is consumed. Yes, 1 electron volt is 1.6 into 10 to the power minus 19 joules. Just see how small unit it is. 1 electron means such small amount of energy. Electrons moving around the orbit. We have heard electrons, they move in a very high speed in the orbits. But see, still the energy possessed by them is too small. Electrons revolving in the orbit. Then next we have different kinds of energy, right? The first type of energy we have a mechanical energy. How do you define a mechanical energy? It is defined as a energy possessed by a body by a virtue of position, configuration, or motion, right? So in case energy, right, it can be described in terms of position from the ground, right? I'm standing right now, so I'm quite higher than the ground. My center of gravity is somewhere on the belly, so my position is higher than the ground, so obviously I possess a mechanical energy. If I move, I am in motion, once again I possess a mechanical energy. Configuration, standing this way, right, standing with the arms folded, these are different configurations. Again, in different configuration we possess a mechanical energy, right? So because of position, because of configuration, because of motion, or because of all three, body will possess a mechanical energy. Spring, you may take an example, right? Spring, when it is under a relaxed condition, its configuration is different. When you compress it, again the configuration becomes different, right? Ball rolling on the ground in motion has a mechanical energy. Something at a height from the ground, its position is different, again has a mechanical energy. Mechanical energy gets classified into two categories, right? First one is potential energy and other one is a kinetic energy. Potential energy, this is a special word given to the energy which is because of the position. It's because of virtue of position. The complete definition we'll discuss in the next slide. And kinetic energy, it is a special word given to the mechanical energy which is only because of motion, virtue of motion. So when we say ball rolling on the ground, it has got mechanical energy for sure, but to be specific, it has also got a kinetic energy. Even saying mechanical energy is not wrong, but to be absolutely perfect, the rolling ball has got a kinetic energy. Compressed spring, for sure, it has got a mechanical energy. Once again, to be specific, it has got a potential energy, right? Next, we have heat energy. You know very well, right? Heat energy, it is the energy that produce in us the sensation of hotness or coldness. You feel hot or you feel cold, it's because of heat energy. Simple definition: light energy, it is a it is an energy, it is the energy, the word would be better, it's the energy that causes in us the sensation of vision. We are able to see the objects, it's because of light energy. The light energy, those waves enters into our eyes, goes to the brain processes it, ultimately we process, ultimately we are able to visualize the object. So light energy. Then we have sound energy, right? You can define it as sound energy. It's the energy that causes in us the sensation of hearing. We call it as a sound energy, right? Sound, when I speak, the energy travels, right? As soon as I speak, the energy is emitted from the mouth, from the vocal cords over here. This organ, it emits the energy. A forced air has got the mechanical energy. That mechanical energy travels through the air and reaches your ears. It produce sensation on the eardrums. Those sensations are carried on to the brain and ultimately you identify the voice. So energy that causes in us the sensation of hearing, we call it as a sound energy. Magnetic energy, the energy possessed by magnets, right? It's called as a magnetic energy. Magnets, they get attracted to each other, they repel each other, it's because of the magnetic energy. Electrical energy, it's the energy possessed by moving electrons. Electrons, when they move, right, due to application of potential difference, electrons, they move because of the application of potential difference. So these moving electrons, they've got a electrical energy. Chemical energy, the energy in the form of chemical bond formed by outermost shell electrons. Outermost shell electrons, they participate in a chemical bond, right? So ultimately chemical energy appears into the compound. The compound, let's say sodium chloride, it has got chemical energy into it, right? When you dissolve the salt, the liquid, the water, it gets slightly heated up. It's because the chemical energy gets liberated out. Sodium chloride salt, when you dissolve, it gets slightly warm because the chemical energy is liberated out. Then next we have nuclear energy. Nuclear energy, it is the energy associated with nucleons. These are not the final definitions, right? Textbooks, many textbooks, they describe those terms in their own words. You can also write in their own words. If it is not possible to describe it in a single sentence, you may use multiple sentences. Nothing wrong in it. It is the energy associated with the nucleons. You can also say energy associated with nuclear reactions, right? When the nuclear reactions happen, large amount of energies are produced. So that is once again a nuclear energy, right? So this is how you can energy associated with the nuclear reaction. Nucleus itself participates, protons and neutrons inside the nucleus, they participate. Ultimately we have a nuclear energy. Next we have a kinetic energy.